The goal of this work is to create a realistic and animatable human body model from 3D scanned data. Using a single scan like this one is not sufficient to capture the range of deformations caused by muscles, bones, and other tissues as the body moves. Therefore, we will need to capture our subject in many different poses. Shown here is a visualization of a cyberware scanner acquiring a straight arm. We use a system of ropes to help the subject remain stationary during the 17-second-long scanning time. This is one of many scans that we will use. In addition to range data, the scanner also acquires color information. We use the color information to determine the location of markers placed on the subject. These markers in turn will be used to find the pose of the arm in each scan. We enhance and localize the markers by applying a dot-finding convolution filter to the color data. We then assign labels to uniquely identify each marker in a user-guided process. We repeat the scanning process for a variety of poses, 36 arm poses, 33 shoulder poses, and 27 torso poses. Next, we want to fit a skeleton to each scan. We need to solve for three things: the pose, the bone translations, and the local marker positions. Here we show the error between our initial skeleton and the observed marker locations for one scan as white lines. We use a quasi-Newtonian optimization to minimize this error. However, the bone lengths and marker positions are common to all scans. Therefore, we actually optimize over all scan poses simultaneously with over 2,000 degrees of freedom in total. This optimization takes approximately half an hour to run. Once we know the true skeleton and the pose for each scan, we create a template subdivision surface to record the deformations. We base this surface on the skeleton by placing its control points in weighted combinations of adjacent joint coordinate frames. As the skeleton moves, the subdivision surface follows. We create a displaced subdivision surface by casting the rays in the normal direction to the subdivision surface and recording the distance to the scanned mesh. Because of the occlusions and grazing angle views while scanning, there are many holes in the mesh. We fill in these holes first with a constant displacement, and then run a curvature minimizing optimization over the filled parts of the displacement map. Each of our datasets samples some part of joint angle space. For instance, the arm dataset contains examples of elbow bend, forearm twist, and wrist angle. In order to create a new pose, we need to interpolate the nearby examples. We use k-nearest neighbor interpolation, where the new mesh displacements are a weighted combination of the displacement values from similar scans. These displacements are applied to the template surface in its new pose. Given a novel set of poses, we find interpolated arm, shoulder, and torso surfaces. The final step is to combine the body parts into a single model by smoothly blending the displacements at the boundaries. We can perform simple editing operations by changing the template surface. Shown here is a torso model that is 20% thinner around all bones. This model is 20% fatter than the original. We will conclude with some animations generated from motion capture data. Stand-in geometry has been added for the head and legs. Here's the same animation again in slow motion. Thanks for watching.